Check it out now, y'all.
nanoHUB-U online instruction.
Hello and welcome back to week 3 of nanoHUB-U's Introduction to Bioelectricity. Today, in this lecture, we begin with a discussion of electrical variables and the roles that they play in cells. Over the course of this week, we're going to be looking into various models, 2 models specifically, the core conductor model and the cable model of biological conductors. So we know how electrical conductors work from our freshman physics. We're going to look at how biological conductors work, and we're going to try to describe biological conductors in terms of electrical conductors that we're more familiar with. And we're going to see how well those models describe what we're looking at and in which ways they fail, and that will then motivate us for next week, where we'll begin discussing the Hodgkin-Huxley equation to see what it is that makes that equation so special and what it is that it accounts for that the models we'll talk about this week don't. But the material in this week is very, very important. The derivations that we will do next week actually build on the models that we begin with here. So it's very important to understand this material and its role in describing biological conductors. So diving right in, let's define a few variables. So if you have a cylindrical conductor, biological conductor, and it's not accidental that I'm choosing a cylindrical conductor. Most of what we want to know about how currents behave in neurons relates to how they propagate down axons. And so axons are cylindrical in structure, so it's easiest if we look at cylindrical conductors. And I'll say more about what role that plays on how we do our math in a few slides. But for now, let's just look at a cylindrical conductor that has a inner diameter A and has a surface area of a given value. It has a length L, and it has a current density that flows outward through that surface area, J. So in terms of current, we're going to be talking about 2 sorts of current. We're going to be talking about current that flows along the outside of the structure, the axon in this case, the cell, the neuron. We're going to be talking about current that flows along the inside. So there's going to be current I out and current I in. But then there's also current that flows perpendicular to those 2 currents, and direction is important. It flows perpendicular, it flows from the inside of the cell to the outside of the cell. And we're going to make some assumptions around that as well. But regarding current, for now, for this slide, we're talking about the current that flows perpendicularly out, and because we're talking about that current as a function of surface area, we're talking about current density. So I is the transmembrane current. I divided by L, the length, gives you K, and K is the variable name that we will use for current per unit length. And I divided by the area, which is 2 pi times the inner diameter times the length, will give you J, which is the current density. Ohm's law, which I'm sure you all know, but let's refresh ourselves here. Ohm's law describes the relationship between a voltage and a current when we know the impedance or the resistance R between or across which that current is flowing. So a current flowing through a resistor R will generate a voltage V. V equals IR. But that resistance can also be an impedance. So the difference between resistance and impedance is that impedance can be complex. So it can have a real and an imaginary value. And imaginary values are how we describe impedance elements like capacitors and inductors. We won't be seeing inductors much in this course, but we will be seeing capacitors often, because the membrane, if you recall, is the phospholipid bilayer acts as a capacitor where you have a higher concentration of positive charged potassium ions on the outside and a higher concentration of negatively charged anions on the inside. And that creates that negative resting membrane voltage. They're separated by an insulator. That's exactly what a capacitor is. It's 2 charged plates with an insulator in the middle. So it will be important to talk about impedance later on in this course. Electric field describes the voltage divided by the distance between 2 points. So if we have a voltage of 10 volts across a distance of 2 meters, we have an electric field of 5 volts per meter. So you divide the voltage by the distance, and that gives you the electric field. And as you take the limit of that electric field as that distance goes to 0, you get to the voltage at a specific individual point, the infinitesimal segment voltage. But for now, the electric field E is equal to V, the voltage, divided by the distance between 2 points. So V divided by A in this case, the radius, gives you the IR, that's the same thing as V from Ohm's law, divided by A. And so we know that the electric field E is equal to IR divided by A, which is nothing other than J, the current density, multiplied by the area, divided by little a, and multiplied times the resistance. So it's J R 2 pi L. That's our equation for electric field, and that'll be quite useful shortly. Continuing on electric field, we can then define part of that equation such that rho, which was the right-hand side of the electric field equation, is equal to R 2 pi L. So the resistance at a specific point times 2 pi times the length. So it's the area, really the surface area, divided by the radius. Multiplied times the resistance, that gives you the resistivity. And that is a material property of the structure that we're looking at. Conductivity is related to resistivity by the ratio. So conductivity is 1 over the resistivity, and conductivity is expressed in Siemens per meter, whereas resistivity is expressed in ohms meters. Then Ohm's law for a conductor can be expressed, instead of as V equals IR, we can express it as J, which is the current density, equals sigma, which is the conductivity, times E, the electric field. It's the same Ohm's law, just using different terms that are more appropriate for the structure that we wish to examine. So before we go any further, though, when we start to look at things as they move through bodies, it's important to talk about direction and dimensions. With regards to direction, to vectors, to the way things flow, we have the Cartesian coordinate system, which is the coordinate system that most of us grow up with and are most familiar with. It ends up being one of the least useful for these sorts of mathematical problems, and I'll tell you why in just a minute. For now, let's refresh. The Cartesian coordinate system involves 3 distinct coordinates, x, y, and z, where you can always tell which way z points by putting your hand along the x-axis, your right hand, it has to be your right hand, along the x-axis, wrapping your fingers in towards the y-axis, and your thumb will always point in the direction of the z-axis. So the x-axis, the y-axis, the z-axis, and these axes can be broken down into unit vectors, where each unit vector has a magnitude of 1, of whatever unit you wish to use, 1 meter or 1 millimeter, regardless of magnitude of 1. And so the x-hat vector is a magnitude of 1 pointing in the x-axis direction. The y-hat unit vector has a magnitude of 1 pointing in the y-axis direction. The z-hat unit vector has a magnitude of 1, and it points in along the z-axis. So if you had coordinates of 1, 1, 1, you would be describing a point in space that was located at 1 on the x-axis, 1 on the y-axis, 1 on the z-axis. And this works very well for describing rectangular objects, which is why it's sometimes known as the rectangular coordinate system. And rectangular objects, typically man-made constructs, are all fine and well, but they're not what we're interested in this course. What we're talking about in this course has curves. And so we can look at the spherical coordinate system. And the spherical coordinate system uses different vectors to describe the exact same point. So instead of using x, y, and z, we drop the axes altogether, and we say that with respect to the origin, you can project the point down onto the xy plane, and instead of calculating the x value and the y value, we're going to calculate phi, which is the angle from the x-axis to that point on the xy plane. Then we're going to calculate theta, which is the angle from the z-axis to that point. And then we're going to calculate the distance from the origin to the point. We're going to call that r, the radius. So you're going to have the phi hat vector pointing along the x-axis from the x-axis in the direction of the y-axis, positive x-axis to positive y-axis. You're going to have the theta hat vector, which points from the positive z-axis down to the negative z-axis. And then you're going to have the R vector, which points from the origin directly out to the point. And this is a very good system for describing spherical objects. So in a spherical object, as you move around the surface of the sphere, your radius, R, is not going to vary. And only your phi and theta hat values are going to vary. And that simplifies our math, as you'll see shortly. And finally, and most usefully for us, the cylindrical coordinate system comes halfway between the Cartesian coordinate system and the spherical coordinate system. So in the cylindrical coordinate system, we retain our z-axis. So we have our x and y axes, but we don't use them anymore. We don't use the x hat and y hat vectors. Instead, any point in space is projected onto the xy plane, just like it was in the spherical coordinate system. And from that, we calculate phi. Phi is the angle from the positive x-axis in the direction of the positive y-axis to the point of interest. In this case, phi hat is pi over 4, or phi is pi over 4 in the phi hat direction. R is the radius taken from the origin to the point projected on the xy plane. So it's not directly to the point, it's to that point projected on the xy plane. Another way of thinking about it is that R is the vector taken from the closest point on the z-axis to the point of interest. And then z is just z, same as it is in the Cartesian coordinate system. It's the elevation. And this is very nice for describing a cylindrical object because it tells you all about the variations in phi go around the circumference of the cylinder. Variations in R move from the inside of the cylinder to the outside of the cylinder. And variations in z move along the length of the cylinder. So in the neuron or in the axon we were talking about earlier, you would expect that the inner and outer currents, which flow axially, would flow exclusively in the z-hat direction. Whereas the membrane current, which flows out through the membrane perpendicular, would flow in the r-hat direction. And that covers all of the membrane current in all possible directions. If we use the Cartesian system, we would have to use both x and y axes to describe radial current. Using the cylindrical, we can use just the r-hat components. And we can observe that in the phi-hat direction, there's no current in the phi-hat direction. And that helps us, again, with the math. And to see why, let's talk about the Dell operator. So the Dell operator is a mathematical operator defined as Dell is equal to the partial derivative with respect to x in the x-hat direction, plus the partial derivative with respect to y in the y-hat direction, plus the partial derivative with respect to z in the z-hat direction. And you can take the Dell operator and you can multiply it in various different ways times different quantities to get different sorts of results. So if you take the Dell operator and you multiply it times, you take the dot product of it with a vector, it'll give you the divergence of that vector. It'll give you a scalar which describes the tendency of that vector to diverge, to spread out. If you take it and you multiply it instead by a scalar, it'll give you a vector, which will give you the gradient. It'll tell you not just the tendency of that to spread out, to thin out, but it'll tell you the direction in which that happens. Remember earlier we talked about diffusion gradients. Well, this is how you calculate a diffusion gradient. And in the middle you have the curl, which is when you take the cross product of the Dell operator and a vector, and that gives you another vector with the magnitude and direction of the tendency of an object to rotate. And this becomes very important when you're looking at magnetic fields, for example, and the relationship between electric and magnetic fields and electromagnetics. But it won't be particularly useful for us in this course. Right now, we're mostly going to talk about divergence and gradients. So the Dell operator, which we have in Cartesian coordinate system here in terms of x hat, y hat, and z hat vectors, can also be expressed in cylindrical and spherical coordinate systems. Because we're using neurons, or the axons of neurons, that have long cylindrical axons, and that's where we want to look at currents, we're going to be using the cylindrical coordinate system to describe our structure, and we're going to be using the Dell operator for cylindrical coordinate systems to find our solutions to our problems. So let's go back to that two-dimensional conductor. You have an inner radius of A, but because the membrane has some thickness little l, we're going to say the outer diameter is going to be A plus little l, where the length is still capital L, big L. and you're still going to have a current density J flowing out. But now we're going to align this, this axon with our coordinate system such that it is coaxial with the z-axis, and so that R describes flow, R hat direction describes flow out of the membrane in any direction out of the membrane, that's so long as it's perpendicular, and phi describes rotation along the surface of the membrane. And therefore we could describe the electric field as the negative value of the divergence, and negative because electric field points in the direction of increasing voltage, and divergence is going to give you the decreasing voltage. So it'll be the negative value of the divergence of the local potential psi, which is a function of R, but it's also a vector because it points in the R hat direction. So we're taking the dot product between two vectors, and that will give us, if we plug in for the Dell operator, that the electric field is equal to the negative of the Dell operator for cylindrical coordinates, which is the partial with respect to R in the R hat direction, plus 1 over the partial with respect to phi in the phi hat direction, plus the partial with respect to z in the z hat direction, dotted with psi sub R, which is in the R hat direction. And because the entirety of this voltage is in the R hat direction, when we take the dot product, R hat dotted with phi hat gives you 0, R hat dotted with z hat gives you 0, and the only term that is left is the R hat dotted with the R hat, and so this is equal to the negative partial derivative of psi with respect to, as a function of R, with respect to R. And that is equal to what we know the electric field to be equal to, which is rho I divided by 2 pi times the radius R multiplied times L. So here is the electric field as a function of the radius. And this is an example of why it's so important to pick your coordinate system carefully. Because if you don't pick your coordinate system carefully, you end up having more of these derivative terms in. If we had done this using a Cartesian coordinate system, the z hat direction would still have canceled, but psi as a function of R would have existed in both the x hat and y hat planes. And so you would have been left with two terms, the x hat term and the y hat term. Using the cylindrical coordinate system, we take advantage of the fact that only one of these directions aligns with variation in the local potential, and so we're reduced to the minimum number of terms, and that makes for the easiest possible math. To then solve that mathematical equation, we take the integral of both sides as we move from the inner radius to the outer radius of the axon membrane. So as we move from the inner radius A to the outer radius A plus L, we integrate both sides. Rho I divided by 2 pi L comes out because it is a constant, and so we only integrate the derivative of psi and 1 over R. And that gives us the negative of psi evaluated at A plus L minus psi evaluated at A is equal to rho I over 2 pi L times the natural logarithm of A plus L minus the natural logarithm of A. And if you remember from our Nernst derivation equation, the subtraction of two natural logarithms leads to a quotient between the two, and so we can reverse the first terms in the equation to give us psi evaluated A minus psi evaluated A plus L, which is the membrane voltage. So it's the voltage inside the cell minus the voltage outside the cell. That's the membrane voltage, is equal to the constant rho I divided by 2 pi L times the natural logarithm of A plus L over A. And if A is much, much greater than L, so if the inner diameter of the membrane is much, much greater than the membrane thickness, which is true for an axon, then this natural logarithm simplifies to L over A. So we have solved for the membrane voltage as a function of the resistivity, the current through the membrane, the infinitesimal thickness of the membrane divided by 2 pi times the length of the segment we're looking at and the inner radius. Some notes. The resistivity, I mentioned before, I'll repeat it again, is a materials property. So the resistivity is not a variable. It is a constant that is defined by the material that you're looking at, by the cell structure that you're looking at. Different neurons might have different resistivities, but for a particular cell, that resistivity is going to be fixed. Now, the resistance may change over time as you open and close ion channels, but the resistivity of the membrane itself will be fixed. Coordinate systems are very important in simplifying the math. If we had used spherical or Cartesian coordinates, we would have ended up with a much more difficult mathematical problem to solve. That integral would have become quite hairy. I encourage you to lay out that integral in Cartesian and spherical coordinates and see how easy or difficult it is to solve for yourselves. But we've worked through the cylindrical, and that's the case which you should remember. Electrically large and electrically small cells, something I want to say here about those. Electrically large cells are cells in which the potential, the voltage at one point along the cell is not necessarily the same as it is at a different point along the cell, because that separation has a given resistance, which requires a particular current to equalize the voltage between those points. Neurons, which is the type of cell that we're going to be looking at throughout this course, are classified as electrically large cells. Other cells, which in some cases include very small neurons, or signals, say, traveling from one point of the soma to the other, behave a lot more like electrically small cells, where if you know the voltage at a particular point along the cell, you know the voltage at every point throughout the cell. So that's a key distinction, but we're going to focus primarily on electrically large cells. And in the next lecture, we're going to begin to derive the equations that relate voltage and current throughout an electrically large cell for a variety of different conditions. And I'll see you then.